Welcome back, engineering students and professionals. Let's jump right into a serious paradox in the world of electromagnetic compatibility. We're pretty much all taught that blocking magnetic fields requires heavy, bulky magnetic materials, right? Things like thick steel or mu metal to just absorb the fields. But what if I told you that a completely non-magnetic material, literally just everyday copper, can act as a near-perfect magnetic shield? It can completely neutralize aggressive magnetic fields so your devices pass those strict FCC emissions tests. Sounds kind of impossible, I know. But in this explainer, we're going to unlock exactly how this works, diving straight into the brilliant physics and mathematics from Henry Ott's foundational EMC engineering texts. By the end of this, you are going to master the practical intuition behind magnetic shielding so you can design cleaner, quieter, and just massively more robust electrical systems. So first, we've got to address the elephant in the room, this huge misconception. A ton of engineers assume copper shields only stop electric fields. They think low-frequency magnetic fields will just ghost right through copper like it's not even there. And honestly, if we just look at the static material properties, they're not totally wrong. But that completely overlooks the dynamic, real-world behavior of slowing currents. Getting this right isn't just some neat physics trivia. It is an absolute, non-negotiable necessity for real-world signal integrity. If we want to stop our cables from radiating noise or protect sensitive receptor circuits from outside interference, we really need to know what happens when current actually starts flowing. To understand how this works, we need to look past the surface and zoom straight inside the physical cable itself. Let's start down at the absolute foundational level. Imagine looking at a cross-section of a single, unshielded wire carrying a current in free space. That's the solid black dot right in the center. The solid lines shooting straight outward, those are the electric field lines. But look at the dashed concentric circles circling the wire. That is the magnetic field. Think of that magnetic field exactly like ripples spreading out in a pond after you toss a stone in. Without any sort of physical barrier, these magnetic ripples just keep radiating outward, totally unimpeded. And they're absolutely ready to couple with any adjacent circuit and cause a nightmare of electromagnetic interference. Now, let's look at a sharp contrast between two different shielding setups. On one side, we've wrapped our center conductor in a non-magnetic copper shield, but we've only grounded it at one single point. Notice what happens here. The solid electric field lines, they hit the shield and stop. Perfect. But those dashed magnetic ripples, they punch right through the copper as if it's completely invisible. But now look at the other setup. The magnetic field outside the shield is completely gone. Zero external fields. Magic, right? But how? We didn't change the material. Instead, we forced a current to flow through the shield that is exactly equal to, but moving in the totally opposite direction of, the current in the center conductor. Think of this exactly like noise-canceling headphones. The copper shield isn't acting like a thick sponge absorbing the magnetic field, not at all. Instead, it's actively generating an equal and opposite anti-field that perfectly cancels out the source field outside the cable. Let's formalize this concept. This noise-canceling antifield is a magnetic shielding mechanism where a non-magnetic shield carries an equal but opposite return current. And by doing so, it generates its own external magnetic field that completely neutralizes the center conductor's field. But to make this magic actually happen, we can't just rely on the copper sitting there. We need a very specific electrical circuit setup to actively force the return current to flow entirely through that shield. If the return current finds another path, like sneaking back through a ground plane, we lose our antifield entirely, and it's like our noise-canceling headphones just got switched off. Let's move to the equivalent circuit so we can see how this actually builds mathematically. Our main source current, which we'll call I1, flows out through the center conductor. But when it hits the load on the far side, that return current has a choice to make. It can either flow back through the shield, which we label IS, or it can return through the ground plane, labeled IG. Think of this like water flowing through pipes. Water naturally wants to take the path of least resistance. Now, since an ideal ground plane basically has zero resistance, and the copper shield definitely has some resistance, why on earth would the current ever choose to go through the shield? Well, to answer that, we've got to dive into the math, specifically looking at the impedance. We can map out exactly where the current goes by setting up a simple mesh equation around the ground loop. It looks like this. 0 equals IS times the quantity j omega Ls plus Rs minus I1 times j omega M. Okay, let's break down every single variable here so it makes physical sense. Is is the current flowing in the shield. J omega represents the complex angular frequency of our signal. Ls is the self-inductance of the shield itself. Rs is the physical resistance of the shield. I1 is our center conductor current, and M is the mutual inductance between that center conductor and the shield. This equation is just balancing the voltage drops around our loop. That J omega M term is absolutely key. It represents the voltage induced right into the shield by the center conductor's own magnetic field. That is our crucial link. And here is where the math simplifies beautifully step by step. Step 1. Because we're dealing with a coaxial geometry, meaning the shield completely physically encloses the center conductor, the mutual inductance M is mathematically exactly equal to the shield's self-inductance Ls. So we just substitute Ls in for M. Step 2. We rearrange our mesh equation so we're solving for the shield current Is. We get Is equals I1 times a fraction. That fraction is J omega over the quantity J omega plus Rs divided by Ls. Step 3. We define that term Rs divided by Ls as our shield cutoff frequency, which we write as omega c. Now the equation simplifies to its final elegant form. Is equals I1 times the fraction J omega over J omega plus omega c. So what does this actually physically mean? Well, at really high frequencies, J omega becomes massive compared to omega c. So that fraction essentially just becomes 1. Therefore, Is approaches I1. The shield current perfectly matches the center current, giving us our flawless, noise-canceling anti-field. So you're probably wondering, how high of a frequency do we actually need to pull this off? The magic rule of thumb number here is 5 times the shield cutoff frequency, or 5 omega c. Once you hit frequencies higher than that, the inductive reactance completely dominates the plain old resistance. The coaxial cable starts acting beautifully as a common mode choke. The mutual inductance physically forces that return current up out of the zero resistance ground plane and pushes it directly into the shield. Let's do a quick real-world example. Say your specific cable geometry gives you a shield cutoff frequency, your omega c, of 1 kilohertz. If you pump a 10 kilohertz signal through it, your J omega term is 10 times bigger than omega c. Looking at our fraction, 10 over 10 plus 1 is practically 1. The math physically guarantees that the shield will carry almost all of that return current. Your noise-canceling anti-field is fully powered up, and that magnetic radiation completely neutralized. But wait, what if you're stuck operating at low frequencies, totally below that cutoff point? Check out this paradigm shift. If we physically disconnect the ground connection at the far end of the circuit, we completely destroy the ground plane path. It's gone. Now, it literally doesn't matter if your signal is 1 hertz or 1 megahertz. 100% of your return current absolutely must flow back through the shield purely because we left it no other physical path. You are forcing Is to exactly equal I1, which guarantees your anti-field is pumping out, completely regardless of your operating frequency. Okay, but before you start aggressively ripping out ground connections to force those shield currents, we really need to talk about a massive pitfall. I like to call this the grounding gotcha, though textbooks formally call it common impedance shield coupling. This is a highly dangerous trap that trips up a ton of experienced engineers, and it will absolutely destroy your system's signal integrity. The real danger happens when you rely on one single physical shield to do 2 jobs: carrying your intended signal return current and absorbing unwanted noise currents induced by random external fields. When one conductor pulls double duty like that, things get ugly fast. Let's analyze this specific edge case back on our equivalent circuit. Imagine your cable is snaking through a super noisy factory floor. Some big external magnetic field nearby induces a nasty, low-frequency noise current, let's label it IS, straight into your shield. Now, because your shield is grounded at both ends to act as your signal return path, this external noise current just flows right along it. The shield is basically acting as a highway, carrying this noise directly into the input of your highly sensitive amplifier. It entirely corrupts your clean signal. Let's look at the mathematical gotcha that explains why this is so devastating. If we sum up the voltages around this input loop, we land on equation 2-32. The input noise voltage, VIN, equals negative J omega MIS plus J omega LSIS plus RSIS. But hey, remember our golden geometry rule from earlier? LS is exactly equal to M. Because those values match perfectly, those 2 inductive voltage terms completely obliterate each other. They cancel out to 0. So we are left with the heavily simplified equation 2-33. VIN equals RSIS. And guys, this is completely unavoidable. Because that noise current is physically flowing through the resistive impedance of the copper shield, it creates a direct physical noise voltage that gets injected directly into your signal path. So what's the actual engineering solution here? You've got to upgrade from a standard coaxial cable to a shielded twisted pair. See, standard coax forces the shield to perform 2 totally conflicting functions, acting as the signal return and acting as the noise barrier. It shares a common impedance, leaving your signal wide open and vulnerable. But a shielded twisted pair
That is a three-conductor system. The two inner twisted wires safely carry the signal and its return, while the completely isolated outer shield handles all those nasty external noise currents. By physically separating the signal path from the noise path, we completely eliminate that common impedance coupling. Problem solved?
All right, let's lock this in with a rapid-fire, three-point recap of the absolute most critical takeaways for your next design. Number 1, non-magnetic shields, like copper, defeat magnetic fields by generating active anti-fields, not by absorbing energy like a sponge. Number 2, remember the math behind equation 231. The shield current naturally matches the inner conductor current when you operate at frequencies above 5 times the shield cutoff frequency, giving you automatic magnetic shielding. And number 3, avoid common impedance coupling at all costs. If you are battling low-frequency noise, strictly separate your signal and noise paths by upgrading from standard coax to a shielded twisted pair.
Henriot actually dedicated his foundational book with an incredible quote from Albert Einstein. Everything should be made as simple as possible, but no simpler. Listen, electromagnetic compatibility can often feel like pure black magic. But when you finally break it down into the fundamental math and physics, it's just a solvable puzzle. So the next time you are routing a critical cable in your system, you have to ask yourself, are you actively generating a protective anti-field, or did you just accidentally build a giant antenna for noise? If you found this breakdown valuable, hit subscribe for more EMC and automotive communication protocol survival guides. Keep learning, keep building, and I will see you in the next explainer.